All right, here we go. So really this is more of the same. The main difference is these problems involve pulling instead of pushing. And honestly, I think the only thing really that I want to talk about here is just talk a little bit about tension. In the notes here, we just use capital T for tension. So yeah, so remember tension is the force applied by a rope or a chain or whatever. We're always going to assume that our ropes are massless and unstretchable, so you don't need to worry about the force required to move the rope. All right. Please remember that under those circumstances, the tension force will be the same at both ends of the rope. Okay. We will frequently be using massless, frictionless pulleys to sort of bend the rope, right? So like in this first example, the hand is pulling the rope this way. That means the rope is pulling the hand this way. And basically, the way I always think of it is the rope acts as a conduit for the force, right? So the rope rope transfers the force from the hand to the box, right? So the hand pulls the rope, which means the rope pulls the box, okay, with some amount of force tension, okay? It is worth noting, in the last video I talked about sines, right? So this is a really good example of this, so check it out. If I call this T, then in my free body diagram, this force, so we have a free body diagram for two different objects, right? One for the box, right? Then you have a separate free body diagram for the hand. We'd have to call this negative T, right? Because they have the same magnitude, but they're in opposite directions, right? So that's a perfect example of what I was talking about the other day. All right, now, notice in this example over here, we've got the pulley is bending the rope, right? So it changes the direction of the force, right? So now instead of, the hand pulling the rope backwards and the rope pulling the box in that same direction, here we've got the rope being pulled down. The pulley bends that force and causes the box to be pulled forwards. Over here, we got kind of the same idea, right? Okay, so tension is the same at both ends. Watch your signs. Pulleys bend the force, or change the direction of the force, I guess is probably a better way to say that. All right, so let's do this example. Why am I on dual screen? I don't know. Let's do that. That's better. Okay, so in the image here, our boxes have masses of, so mass A is got a mass of 3m. This guy has a mass of just m, and box C has a mass of 2m. All right? The applied force is 12 mg. So over here, we've got this force being applied just to box C, and it's got a magnitude of 12 mg. All right? And so what we need to do is we need to find both the tension in that string there that's labeled with T, and find the acceleration of box A, which is kind of silly, right? Because everything's going to have the same acceleration, right? So I guess the first thing I would do is I would look at the system as a whole. So here's box A, B, and C combined. They're going to have a total mass of 6m. The only external force is force F, which has a magnitude of 12 mg. And so I can find my acceleration, right? The acceleration of objects A, B, and C is going to be the net force on object A, B, and C over the mass of objects A, B, and C, which is 12 mg over 6m. That gives us 2g. All right, so there you go. So now we've got the acceleration, right? And so that was actually this. Right, so now we can go back and find our tension. All right, so to find the tension, we need to pick one of the two boxes, okay, which are acted on by that tension force. And I'm looking at box B and thinking there are two tension forces acting on box B, right? And this tension force over here, I don't know. So it probably makes more sense for us to focus on box C, okay? So let's take a minute and do that. So we just figured out that the acceleration of all three boxes, including box C, is 2g. All right, so if I draw my box C, it's got a mass of 2m. There's a forwards force on it of 12 mg, and the mysterious tension force, right? Notice, negative. Got to manufacture that negative sign, right? Okay, so what do we want to do here? We got to go net force equals net force, right? So mass times acceleration equals force minus tension. So you're going to get 4 mg equals 12 mg minus t. Subtract, you get 8 mg equals negative t. So cancel the negatives. There you go. There's your tension force, 8 mg. All right. So nothing mind-blowing there. We've done these before. All right. Now, the next example is the exact same thing, but friction is added in. And I guess I want to point out two things about this example. So let me do that. All right. So here we go. Do this. All right. All right. So exact same setup. The only difference is this time we've got friction. Okay. So I'm going to do something kind of the hard way to show you that you don't have to do it the hard way. All right, so here's the deal. Let's do this. So now, because of friction, we got to think about our vertical forces, right? Because of normal force, right? So let's see. So here we go. So this guy has mass of 3m. This guy has a mass of m. This guy has a mass of 2m. Let's go ahead and put in our forces of gravity. We're going to have negative 3 mg here. We're going to have negative mg here. We're going to have negative 2 mg here. We're going to have normal forces to cancel that out. Positive 3 mg, positive mg, positive 2 mg, and then you're going to have friction forces, right? So let's do this. Let's find, for each of our boxes, let's find our force of friction static maximum, okay, for each box, all right? So our coefficient of friction is 0.4. So for this one, it's going to be 0.4 times 3 mg, right? Coefficient of friction times my normal force. All right, so that would be, you know, against the motion, presumably, right? I don't want to put my arrow in yet because we don't know what's going on here yet. For this one, for the second box, we're going to have 0.4 times its normal force, which is just mg. And for this last box, we're going to have 0.4 times its normal force, which is 2 mg, right? And so the idea is, I guess we can draw them in. So you're going to have a force of friction here, a force of friction here, a force of friction here, to give you sort of a total force of friction. I'm going to use terrible notation. Net force of friction static max is going to be these guys added up, right? Oh, but look, that's just 0.4 times 3 mg plus mg plus 2 mg. Oops, I forgot mg here, didn't I? Which is exactly the same as if I treated this all as one big box, okay? And you can do that as long as all of the objects have the same coefficients of friction, okay? So, long story short, you end up getting 0.4 times 6 mg, which is 2.4 mg. Okay, so that's our total force of friction. And since we know that our force over here is 12 mg, this is not going to be enough force to keep it at rest, right? So that means we must be dealing with static friction. I'm sorry, dealing with kinetic friction, right? So let's do our kinetic friction. FFK is going to be 0.3 mg. Shoot. Because our coefficient is 0.3, right? From over here. So 0.3 times 3 mg, 0.3 times mg, and 0.3 times 2 mg. We're going to need these individual forces because we're going to have to look at box C again, okay? So that's the deal. All right, so now let me do this. I am unhappy that I drew a circle there. Let's do that again. All right, so here's our whole system. Boxes A, B, and C. It's got a total mass of 6 mg. We've already decided that our force of 12 mg was more than our static friction could handle. So find your kinetic friction. That's going to be, oh shoot, man, sorry. This should just be 6m, and our force of gravity should be 6 mg, right? Which means that our normal force is 6 mg. And so your force of friction is 0.3 times that, which is 1.8 mg. So now I can find my acceleration, right? So net force equals net force. So I get mass times acceleration equals 12 mg minus 1.8 mg divided out, and the acceleration ends up being 1.7 g. All right, so we got less acceleration now because there's friction, right? The last example, it was 2g. Now it's 1.7 g. Okay, so you do get less acceleration. Let's find our tension force. Okay? So to find the tension force, we need to look at just one of the blocks. All right, and for the same reason as before, I'm going to look at block C. Okay, so let's take a look at block C. Here we go. Here's our block C. It's got a mass of 2m. Force of gravity is negative 2 mg. Normal force is positive 2 mg. We've still got this force over here of 12 mg. We're going to have friction, which is why I went through and did this. So there's our friction. So that's what, 0.6 mg? And negative t, right? So let's see what happens here. So, oops. So here's my free body diagram, right? Why my board feels very cluttered here. All right, and we know our acceleration, right? So here we go. Net force equals net force. So our mass is 2m. Our acceleration is 1.7 g. That's got to equal our total force, which is 12 mg minus 0.6 mg for friction minus our tension. All right, and solve it. And what's wild? You get 8 mg again. So weirdly, the friction didn't affect the tension in the rope, which is really interesting. I don't know that I have anything to say about it, except that that's a surprising result. Okay? All right, so like I say, not a whole lot new here. This is a tough chapter to kind of split up into sections because it's really a lot of the same, but I didn't want you to have a zillion homework assignments on one thing. So I'm going to shut up now because I'm just rambling. There you go. Next video is longer though, and new stuff, so buckle up.